Ben elledim yani. Mail atmışlar. Mail açmışlar. Bir linki açsana bakayım.
Görüyorum abi, biliyorum.
Şuradan oradaki 2 numaralı mikrofonu ayarlayıp adam ben
Modelleri
2 numaralı mikrofon var şeyin üstünde.
tamam.
Onu ayarlayıp aşağıya. Aynen.
Başlamadan şu an Paris Amerikan Koleji öğrencileriyle canlı bağlantıda istiyorsanız onlara bir merhaba diyelim. Merhaba. Evet, buyuruyorlar.
Çalışmıyor mu?
Alo.
Ha değişti.
Yayında. Hayır, yayında. Yayın başladı. Şu an yayında. Yayın başladı.
Today we are welcoming Arzu Çelik, Associate Professor of Molecular Biology and Genetics at Boğaziçi University. We thank her for being with us regardless of her busy schedule. And before we welcome her to the stage, she is already on stage, but we would like to give you some information about her career.
She started her education at Boğaziçi University in 1989, getting her Master of Science degree in 1995. After attending University of Cologne and University of New York, she returned to Boğaziçi University, where she's an associate professor since 2012. She has published many articles and was honored with several awards. We are also delighted to inform you that the Tarsus American College will be joining us online via live stream. We now welcome Arzu Çelik to conduct her experiment.
Okay, hello. Okay, good morning everyone. Thank you for the invitation. I'm really delighted to be here with you guys. And today I want to tell you a little bit about what I'm doing and what I'm interested in and why I'm studying Drosophila melanogaster. And then we're going to do like a short experiment, and I'll show you how we can extract and visualize polychain chromosomes of flies. So I started my career, as we heard, from Deniz and Ulaş. Okay, sorry. So I started my career here in Boğaziçi University, and so at that time research in Turkey was not very possible, or was very limited, let's say. So we were doing, not many people were doing kind of basic science and looking at the function of genes and proteins. So since I was interested in how certain mutations in the DNA cause certain phenotypes, cause certain diseases, I wanted to go abroad to learn more about functional studies. And but I always had in mind to come back and establish new research areas in Turkey. And that's why after doing my PhD using zebrafish as a model organism, I switched to flies, which are a much more amenable system to do genetic and molecular biology research. And so why are we using model organisms in biological research? Is obviously we're all interested in how we work, like how our bodies are established. So unfortunately, the slides are not ready yet. So when you think about, we all start out from a single cell, from a zygote, so from the fusion of a sperm and an egg cell, and then there is one single cell which then divides to form an entire organism. So we all started out as a single cell. So I was always fascinated about how does this happen. So how by from one cell, by simple cell division, and I think you learned about mitosis. So we have one single cell which has one DNA molecule, and all the cells in our body have the same DNA molecule. So it's not different in any of our cells, but how from one single cell we generate all kinds of different types of cells in the body. So when you look at the different cell types in our body, we have more than 250 different types that range from nerve cells to heart cell to liver cell. So all these cells have acquired different functions. Okay, so our brain cells have a different function than our heart cell or another muscle cell. So how does this happen during development? So this is what I'm really fascinated with. And we know that these processes, so how a cell becomes different from another cell, this happens during development. So during the process of one single cell giving rise to a whole organism. So this is my research area, so this is what I'm trying to solve. And obviously I'm very interested in how this works in humans. But you know that we can't do experiments on humans. We can't even watch the embryo grow, although recently people were able, using microscopic techniques, to watch how an embryo grows in a human body. So these kinds of things, working on development is very difficult on animals where the embryo grows inside the womb of the mother. That's why we can switch and go and use some of the organisms like flies and zebrafish or xenopus, where the embryos develop outside of the mother. So we can really take the embryos when they're an egg and go under the microscope and watch how these cells are dividing. So you really can see like how from one single zebrafish embryo cell, from the zygote, we generate 2 cells, we generate 4 cells. So if you sit half an hour at the microscope, you can see how the cell divides, which is really amazing, I think. And it would be nice to have the slides. I had some nice pictures. So why am I using Drosophila? So Drosophila melanogaster, you might know or might not know. So this is what we call the little flies you see in your kitchen. Then you have some fruits. When there are a lot of fruits, when the summer you see all these little flies in your kitchen. So these are the flies we are working on, and we are interested in how the brain develops in those flies. So those flies have a brain, yes, I get this question a lot. But flies have a brain, and interestingly, flies are really very similar to humans, even to vertebrates. So flies are really similar to, although they're insects, they're very similar to vertebrates. It's hard to believe, but if you look on the genetic scale, so if you go to the DNA and look, so how similar is a fly to a human, so we can say it's about 75%. In particular, if you look at all the disease genes, so all the genes that, when mutated, give rise to a genetic disorder in humans, are conserved in flies. So we use flies for basic research to figure out how cells become different and how the brain develops. But we also are using flies to try to develop some models for human disorders. So we try basically to find the same gene in the fly that is mutated in a human disorder, and then we try to generate a fly model that recapitulates, or that shows the same phenotypes as the diseased person. And once we have that, so we can use flies very nicely to do some drug discovery screens. So we can try to test tons of drugs and millions of drugs on this fly model and look if any of these drugs we have tested on the flies are helping to improve the phenotypes. So that's what I already told you. I'm going to skip these quite quickly. So I said, so we are interested in how cells differentiate. So during cell division, we normally generate, from one cell we generate 2 cells that are exactly the same. They have exactly the same DNA, but during development, the cells start to differentiate. The cells start to differentiate and generate all different types of cells, like nerve cells, muscle cells, bone cells, but they all have the same DNA. So why do cells look different and have different functions? So what is the difference between these cells, although they all have the same DNA? And this is actually because they use different parts of their genome. So they express different types of genes. And I told you that we're using Drosophila. So this is a highly magnified picture of flies, so they're really small, and I have some with me, so you can look at them. And I told you they are very, so many of the principles in flies are very similar to principles in humans. And these include all these systems, like, so we are interested most in the nervous system, and all the basic principles of the nervous system, the digestive system, the body organization, or things like the circulation, excretion, the skeletal muscles. So they're all very similar in flies. So this is basically why you can use the fly to try to understand the genes that are necessary for the establishment of the nervous system, for example, or for the blood circulation, etc. So when we learn something in flies, we can then adapt this directly to the human. So I'm going to skip these slides because I already talked about this. But I was right here talking about why we use Drosophila. Because, as I said, many of the fundamental aspects are very similar in flies and humans. So the disease genes are conserved, and we know exactly the genome of flies. So this genome has been sequenced, we know every single base in the fly. And we know actually much more about the fly genome than we know about the human genome and the function of genes. Then flies are good because they grow very fast, so the life cycle is short. So in 10 days we have the next generation of flies. So basically a new experiment and then the next generation. What has happened? So we can get a large number of progeny. So in humans, we don't give a lot of progeny. So if you would study humans, we have 1 or 2 kids, sometimes a little bit more, but in flies, so every mother lays about 400 eggs. So this has many, so they have many progeny, so you can study the genetics much better. And there are very powerful genetic approaches you can use in flies to do very specific and very complicated experiments to answer interesting questions. Then you can do behavioral studies. So flies can be used in behavioral studies. You can ask them to distinguish between different colors, between different odors. You can perform tests and test how they are walking. So if you study a disease, for example, that's affecting the muscle, then flies don't fly anymore, but they mostly walk. And then you can try to find some drugs that will help these flies to move better and to fly again. So in many cases, it has been shown that these drugs will also help humans. So as I said, I'm interested in developmental biology, so from the process how we get from one cell to a whole organism. So many of you might not care about it, but actually it's quite important to learn a lot about basic science, to learn about, because some people, my father always ask me, so what do you care about the fly, and if it has a brain and how its brain develops. But all the new technologies have been arose basically from basic science, and in many cases we cannot predict what the research we're doing today will be used for in 10 or 20 years. So, and developmental biology is actually very interesting. Recently, all the information we have gathered in developmental biology has helped in, for example, stem cell research, but it's also fundamental for cancer research. Because anything that goes wrong during development, so if some process during development, during the growth of the embryo goes wrong, then this will cause a disease. And if we know, the better we know how it normally works, the easier for us it will be to design drugs to understand what is going wrong during a particular disorder. So that's why it's important to understand first the basics. So how do we see color? How do we smell? How do these cells become different? So these are really very basic questions, but these will all help us later to understand disease states. And for example, like a very famous fly geneticist, so a person like me who has only worked on flies for his whole life, has then switched, he has gathered so much knowledge from these basic developmental processes that he tried to apply these to other systems, to vertebrate systems, and 2 or 3 years ago, they really managed to start to do some stem cell research, and from simple stem cells, they managed to generate little brains in a dish. So this was a very interesting study. So this is a picture of such a brain that has been grown in a dish. So it doesn't really look like the brain you imagine, but this is a mouse brain, which obviously looks almost like our own brain. But in the dish, this has been brought from the stem cells, and when you look at the corners, for example, you see that it has like these foldings and it's generating foldings. And in cell culture, what you can do then, I mean, you do all these tests to show, okay, how similar is this structure that I have generated? How similar is this to the original structure, to the real brain? And actually, it looks very, very much like the human brain or like the original mouse brain, because it has all the cells, so they were able to generate all the cells that make up the brain, all the right connections. So it is really now a very good system to use as a model and study, so how does the brain work. So now we can generate our own little brains in the dish and then try to find drugs maybe to study some genetic disorders that affect the brain. And you can try to see how certain drugs will affect these little mini brains in the dish. Okay. And once you find something, then you can go to the human subjects and try to give them the drugs and see if they show the same effect. So this is, but how this research started is really a fly person doing some developmental biology in his lab and trying to see how cells are dividing and how cells are differentiating into different types of cells. And this helped him to now do this really fundamental breakthrough kind of research. It's just a small example of what you can learn from basic science and then go a little bit more to applied science. Of course, in the short amount of time that we have here, we can only do small experiments, and how this started out was we can do some polyethylene chromosome extraction, and that's why I'm here. So why polyethylene chromosomes? So what are polyethylene chromosomes? You probably know, but these are oversized chromosomes. So when we look at flies have only 4 chromosomes. We have much more, but flies have a smaller number of chromosomes, although, as I said, they carry all the genes that we have as well, in a smaller amount of DNA. And polyethylene chromosomes are really specialized chromosomes. So you learn about mitosis, I heard, and that cells, before they divide, they duplicate their DNA. Normally, so the DNA is duplicated, so each chromosome is copied, and then in the end the cell will divide. Once everything has happened, the cell will divide to generate 2 cells. So what's happening here is that the cell is duplicating its chromosome, but it's not dividing in the end. So it keeps undergoing replication, so it is replicating the DNA, but the DNA is not separating into 2 cells, but it's the sister chromatids keep attached to each other. And then in the end, we have this enormously large chromosomes, which have many, many copies of DNA. And the cells are also getting large, so we have huge cells that contain many copies, 40 copies or so, of DNA. So why would a cell do that? What do you think? Why does a cell not divide? Yes?
Maybe a damaged DNA causes
So the cells are not going to apoptosis, so it's a normal process. They keep dividing and not, they keep replicating but not dividing. But if normally, I mean, in the normal case, if a cell would do that, then it would be bad. I mean, like for example, in cancer, what happens is that the cell continues to divide all the time without stopping. So it's not stopping the process. In this case, it's just doing the replication part, but not the division part. So it's just growing in size, but it's not like a real cancer, as you thought. Yes?
Is it like the G0 phase in humans, like nerve cells and muscles? G1 and G2 phase.
Yeah, I mean, so cells get arrested in that case. Here they're not arrested. So they do this normally, and the reason is because they need, for for some gene, they need more of a certain gene product. So they want to increase their metabolic activity. So normally imagine you have 2 copies of a gene, so there's a certain amount of product you can generate if you have only 2 copies. But if you have 40 copies of a gene, you can generate 40 times more than a cell that has only 2 copies. Okay? So this doesn't happen in all cells in the fly, so there are specialized certain tissues adapt to their requirements of to the needs of the cell. And in the salivary gland, this is what happens. So the cell is increasing its copy number, or the number of chromosomes, and so it can generate more product of certain genes. So this is how it looks like. You probably have seen pictures of this. So this is actually what we want to extract today. What you see here are the chromatids, and actually all the chromosomes, all the 4 chromosomes of the fly are attached, which is also not normal, but doesn't happen in all the cells, but in these cells, these chromosomes get attached to each other, and you can visualize the DNA by staining it with certain stains, and here we're going to use this acetoorsein. So this is some dye that can bind DNA and then visualize it. And you see that there are some banding patterns. You see some black areas and some white areas in these chromosomes. And the black areas are areas that are not very active. So there is not, it usually doesn't contain genes or regions of the DNA that are not actively transcribed, whereas the white areas are regions where there is active transcription. So from these areas, DNA is synthesized or RNA is synthesized and turned into protein. In some areas you see so little puff-like structures. So these are very, very active areas where a lot of RNA transcription is happening. So, yes, in the interest of time, I have to continue now. So we want to start some extraction of salivary glands. And I have brought some larvae in a tube. So these are these little midgets. So what I basically will do is I will take these larvae and then with some forceps I will rip them into 2 parts. So this is something, if you're interested in biology, you have to know for yourself if you would be able to kill animals, because in the research this is something we're doing. It's going to work, I'm sure. So what I'm doing right now, I take some saline solution. So this is just to provide a nice environment for flies and for the larvae. I have a plate like this, which we call dissection plate, where I'll put, and it's black so I can see the tissues better because they're all white. And I put a little droplet of this solution on this dissection pad. So for this purpose, I I will use a dissecting microscope. So here the magnification is not so high, but it's a binocular microscope where I don't magnify so high, it's like about 10x. But this will help me to see the whole organism and do the dissection easily. Now you're there. So now we're looking at the pad. And this is the little water droplets I put. So I will take some, with the forceps, I will take some larvae out of this tube and put it right in there. So it has two ends, obviously, so it has a mouth part. So there's that little back part here. So it won't like the forceps, so it will go back. And this is the back part of the larvae. And then so I will take one of the forceps and hold the larvae in the middle. Then I will try to grab the mouth part with the other ends, the other forceps. Okay, when I see it focus, you don't see it focus. This is little eye. Okay, let's go. Okay, so all the interior parts are, this was not very good. I'll try the next one. You see a lot of the interior part of the eye, but here, this is one of the salivary glands. Already fainted, I hope. This operation. This is the other one. are the salivary glands, and the whiter parts are the whiter parts are some fat bodies that are attached. We also have to remove those before doing the staining. What we do next is we take the salivary glands onto some microscope slide, and then we add our staining solution. So this blue solution I have been showing you, and that will help to visualize these bands that we've been seeing. So we take this salivary glands and put them on the slide. Now they're on the slide. Slide, and I take my blue solution here and add a little bit to so this has to stand for 15 minutes. And then we're going to add a cover slip and squeeze those salivary glands so that the DNA can be seen. So we put them into the solution. Now let's take this cover glass, and I will put this on the slide. And then we will squeeze it a bit. So we have to wait 15 minutes, and then I will just press a little bit without breaking the glass because it's very thin, so you have to be careful there, not too much pressure. But that will basically open up the cells, and the DNA, or the protein chromosomes, will be separated. And we have done this before here, but a little problem with the camera. So here we're looking at the hundreds or 1,000 time magnification of the slides which I did before. But it's not really focusing very well. So we're missing a little adapter, that's why we can't focus very well. I don't know if you can see. So here are some bands. I mean, from here it looks much better. So if you really want to see it, I would love to come up here and look at them directly. It doesn't look great, but I hope you can see here a little bit the chromosomes and how it winds. So here these are the chromosome strands, and you see some of the bands if you look very carefully. But as I said, you can all come here and have a look if you want. Mm-hmm. Yeah, please.
Ask any questions? Do you have any questions to our
It could be anything. It doesn't have to be related to flies.
genetics?
Yes.
Can you give an example of a brain disease that you or I don't know, by using this technique was cured?
Was cured.
Yeah.
I know a lot of examples of cancer that were cured by doing tests and generating models in flies. Brain disease. So we are currently, for example, trying to do a central nervous system disease or muscle central nervous interaction disorder. We're trying to generate the model for that, and we have now cloned the gene of the human version of the gene in flies. And normally, like a very critical experiment is where we exchange the fly gene with the human gene. So we put the human gene into the fly mutant and try to see if this rescues the phenotypes, which is the ultimate example of showing that these genes are performing the same function. And the next step will be doing the drug screen. So we're just setting up this drug screen facility. On top of my head, I don't know of a brain disease example, but certain cancers have been, very rare cancers have been cured by generating the models in flies. And there are some companies in the States, where again a friend of mine is working, for example, and they are trying to generate personalized models of every individual, because cancer is a very multifactorial disease. So every patient has different mutations in different genes. So they are trying to generate models for every patient because, as you know, the major problem with drugs is that the same drug does not cure every person. And this is because a lot of mutations, people have different mutations. So this is why it's so difficult to find a cure for cancer.
So is the process is like this? You take a human gene and you put it in, you replace it with the fly's gene, and you give, I don't know, the required medicine to the fly, and you observe the effects and you implement it. Okay, thank you.
But in between, you have also, drug discovery is a very long process. You have usually to go to phase 1, phase 2, so this takes 10 to 20 years. And that's why in Turkey, drug companies do not do that. So we would love them to do this, but the companies' budgets are too low to invest in us. So this is a bit sad. So in Turkey, this is missing. When we talk to some drug companies, but the budget of all the drug companies in Turkey together, if you think of the big ones, Aptigra and Eczacıbaşı, it's not enough to develop one drug. The whole budget, the money they have together is not enough to develop one drug from scratch. So that's why you have to go abroad. People are really trying to do this. I think it's very cool, and I think this is something that Turkey should invest in, because we have, when you look at our plant diversity, so we have a very high plant diversity, and the plant extracts are very often used to generate drugs. And I think if you would do some systematic search, we would find drugs that are really only found here. And I think this is a path that we should follow to find some new drugs to new diseases. And not everybody's using these FDA-approved drugs. Everybody's using the same chemicals to screen for effectors. But I think this would be a much better way to go. Yes.
I have a question for you. Can brain
brain diseases are a bit difficult because of the blood-brain barrier. You know that even if you find a drug, so the way how you give it to the human is very important. So if you give it through the blood, because there's this blood-brain barrier, and so it's like it's like a skin that protects the brain from everything, from the outside. So you don't let everything in. And so the brain is really a very difficult part to cure. Gene therapy in general has not been working so well so far. I think the way it works well is with enzymes. For example, and it depends on which gene is mutated or which protein is not working. So if it's an enzyme, it is much easier to correct for the enzyme than for any other gene. There's still much work needed to figure it out with the brain disorders.
Thank you.
Oh, okay. You're welcome. I think it was longer than expected, as usual.
Okay, let's run to the classes. Thank you.
You're welcome. Ciao.